Hello and welcome. It is Friday night here in New York City, which is not normally what I would think of as prime video recording time, but my wife is away, my kids are asleep. It's not that late yet, and I am still in training for the competition on Tuesday, so I thought, let's do a quick one. So I've grabbed a problem from the FMWC Open last year. This one is based on the game of Snake. So I'll do a very quick intro and then try and zip through the video. I don't promise to get to the end of this one because the end of this one is quite hard. But let's take a look. So this problem is based on the game of Snake, from you might remember from your old Nokia phone. Snake crawls around the grid, tries to eat apples. If it crashes into the wall, it loses. If it crashes into its own tail, like if it went like that, boom, then it loses. And yeah, well, the tasks get trickier as we go along. So level 1, you just have to figure out where does the snake go. It won't hit a wall, won't hit itself, just where does it end up after these 5 moves. Task 2, there are no apples. The game will be over as soon as a snake hits a wall. There are 50 moves. Figure out how many moves will it last before it hits a wall. Okay. Level 3, apples appear on the screen. So these are the 20 apples that appear in order, and if you remember the rules of Snake, that means one apple appears here first, then when you get that, an apple appears here, when you get that, an apple appears here, and so on. For each of the games, the apples will appear in the same cells and in the same order, so this is the list of apples for every game, but you make a different set of moves in every game, and so you have to figure out how many apples do you manage to eat before you hit a wall. And then level 4, so this one you are, in this one you're just kind of making random moves that have nothing to do with the apples. In level 4 you're making moves that are determined by the locations of the apples. So if an apple appears in K2, you go directly to K2, then you go directly to I13, then to C14, C9, E20. And there's some details about how that works. Specifically, you take the most efficient route, meaning you minimize the number of cells and the number of turns. So in other words, let's say we're here, I get to this apple. If the next apple is over here, then there's 2 routes from here to here, there's lots of routes from here to here that would minimize the number of cells, basically anything that kind of follows a path. Sorry, I can't do it that way, but anything that follows a path like that would minimize the number of cells, basically as long as it never goes up outside this box and as long as it never goes right. But so also minimizing turns means that if you start off coming down here, you'd keep on going down until you get to the level you're going, and then you'd turn across. And if the apple appears up here, then you'd first turn this way, then turn this way, because that's the fewest turns you can do it in. So it's the fewest cells and the fewest turns. Now this version of the case is actually one that I did for testing, so it's not exactly the same as the final one. I think based on the testing, the final one ended up specifying that an apple will never appear directly behind the snake because the directions were a little ambiguous. You know, if you hit it here and then the next apple appears up here, you could either turn this way and go up, or you could turn this way and go up, and that might change the shape of the game later. But we'll assume an apple never appears behind the snake. So you basically have to make your way to each of these 4 apples in turn, and the question is how many cells will you travel to eat all of those apples. And then the last level is properly hard. So this is, you're chasing after 50 different apples, but now the snake is able to hit itself. Because it's always aiming for an apple, it will never hit a wall. You assume perfect control. So the question is, how long can it go on following that, minimum cells, minimum turns algorithm until it hits itself? That one is quite a lot harder. So like I said, that's the one I probably won't get to. So that's the introduction. Let's dive on in. So level 1, no apples. Snake appears in A1, won't hit a wall. What's the address of the cell at which the snake will find itself after the 5th move? So I think we actually have all the direction arrows put together up here. So I'm going to take those and paste transpose them down here. And I'm going to figure out how many moves do we make down, up, left, and right. Let's just take that format as well. So then we're going to say equals sum if right of these 5 equals this. And sorry, I'm going to lock in these columns and that row so that I can copy this down and across. If that is the case, then left of that same, sorry, where am I? Left of this, of this same group of 5 cells, and we're going to want, I don't see any double digit, oh yeah, there's double digit moves, so otherwise we could just say left, but we're going to want to say length of that -1 to allow, so there's, in other words, the arrow at the end is always just 1 character, but the number of steps could be 2 digits. So left that -1 times 1, and otherwise 0. And then we sum those up. So we move a total of 11 squares down. Does that check out? 3 plus 8, yes, is 11. We move 0 squares up, 0 squares left, and 16 squares right. That's 3 plus 9 plus 4 is 16. Yes, good. So then I'll just copy that down here. So then, in the end, how many squares down and how many squares right am I? Well, it's going to be 1 plus the number, sorry, let's just delete this. 1 plus the number that you move down minus the number that you move up is going to be how far down you are, and right is going to be 1, sorry, equals 1 plus the number that you move to the right minus the number that you move to the left. And then we need to convert that back into a location. So let's see, the downs are the letters. So to convert the number of downs into a letter, I always mention this in these videos, you can build a lookup table, but your fastest way is to have code and char. So in other words, A, if you use code of that, it'll tell you that's ASCII code or Unicode or whatever, I think it's ASCII, number 65, and if you use char, that'll change the code back into a letter. So then if you want F, that's number 70, and you can convert it back. So in other words, if I'm I've done 1 plus, so in other words, A is 1, B is 2, all the way down to L is 12. So we're just going to say equals char of how far down you are plus, so A is 65, so I want to add 64 to my index. So that gives me an L, and then that ampersand, how far to the right you are, because the number is how far to the right you are. So that gets you to L12. Copy that down, and we'll just put that up here and check. That should reproduce L17 when I paste that in, and it does. So that's probably working. So we move on. Okay, next one. No apples. The snake initially appears in cell A1. The game will be over as soon as the snake hits a wall. How many moves will the game last before the snake hits a wall? Okay, so in this case, I think I want to have a separate calc sheet. And let's see, I'll start off working example 2, and I'm going to XLOOKUP this, and I think the next one has 50 moves as well, so I'll just use that same setup format in there, returning from the set of moves, and I'll lock that in. Actually, I don't need to lock it in because I'm just having one dynamic array, but anyway, and then I'm going to transpose that to lay them out vertically. So I'll call that move. I'll just have move number in case I need to reference that. That's going to be sequence 50. And then I will have, I guess, write down. So, no, let's just do what we had before with the 4 arrows. So we're going to say if right this equals this, then left, not keft, left, this, ln that, -1, otherwise 0. Oh, yeah. So the reason that some of these are aligning left and the others are aligning right is because the text that it's extracting from the string here, it's keeping as text, which is aligning left, and the 0 is a number aligning right. So that's just a little reminder to myself that I need to multiply this by 1. I don't really need to do that because I'm going to add and subtract it, and then it'll kind of force it to treat itself as 1, but whatever, it's fine. So now how far right and how far down? Well, we know that we start off at 1, 1. I'll just, format as an assumption. And then, so how far right is that, plus how far you move to the right, minus how far you move to the left, and how far down is that, plus how far you move down, minus how far you move up. And then I just need to find the first one of these that's out of bounds, and it's pretty easy to spot in this case, and it's on move 4, which I think is what, sorry, back up. Yes, move 4 is the answer we're looking for here. So I just want to say wall question mark. And so how am I going to do this? So if down, oops. So if down is more than 12, or if right is more than 20, or if either of them is less than 0. So I'm going to say or min this is less than or equal to 0. Down is greater than 12, right is greater than 20. So if any of those is true, then we've hit a wall. And that's fine. Okay, so then I want to say first wall. I'm going to say min ifs. So the smallest of these where this is true. And that's 4, and then I want to data table that. So basically just want to say, what does that 4 become if I replace this example 2 with 16, 17, 18, 19, yada, yada, yada. So, sorry, 16, 17 down to 30. So I'm going to say sequence. I want 15 rows starting at 16. That'll give me 16 to 30. Bump that down 1, link that there. Alt DT, my column input cell is this picker up here. And then refresh the calculations. Copy. Alt S, Alt L. Paste the links in there. And that worked on the example, so I feel good about that. So moving on. Level 3. Apples appear on the screen. The snake can't hit itself. The apples appear in this order. Only one apple can appear on the screen at the same time. The snake starts the game in cell A1. If it hits a wall, the game is over. How many apples does it eat during the first 50 moves or before hitting a wall? So let's just go to example 3. And in this case, we actually make it the whole way along without hitting a wall. So it's just a question of how many apples we get. Okay, so oh yeah, so I remember there's a little twist in this which I actually missed the first time round. So if you scan across here, if there was never 2 consecutive apples in either the same row or the same column, then your logic here is much simpler, because one move can only ever take 1 apple. So in other words, if I move across the grid here and I catch an apple, well, the rest of that move will definitely not get another apple, because the next apple is not in the same row or in the same column. So whether I come at it this way or this way doesn't matter. But if you scan across, there's no repeat letter, so I, L, F, I, J, D, etc. But there are actually 2 places where there's a repeat number. So F16 and E16, J16 and I16. So in those cases, if you go far enough, and if you're traveling in the right direction, so that if you're traveling from I guess the letters go down, right? I think yes, the letters go down. So if you're traveling from the bottom to the top, then you'll hit F16 before E16, so you'd eat both of them. If you're traveling from the top to the bottom, then you'd hit F16, and then you'd have to come back around to get E16. It actually doesn't mention it in the instructions here, but it does mention it in the instructions somewhere else, that if in rare cases an apple appears on a cell that is currently occupied by part of the snake, then it does not count as being eaten by the snake. So the head of the snake still has to get back around to that cell. So in other words, in the case where you have F16 and then E16, so if you come down here, eat F16, then E16 appears here. It's not on the head of the snake, so you'll have to kind of come back around at some later point to get that. Anyway, so basically what I'm saying is, because there are a couple of column repeats here, the logic on this is more complicated. So I'm going to start off with a logic that only handles one apple at a time, and then if I still have the time and energy by the time I've done that, I will modify it. The good news is there's never three. There's never a possibility that the same single move in one direction, like that this, say 15 across, would hit 3 apples. The most it could ever hit is 2. So that kind of makes our lives a little easier. So let's just open up a little more space here. All the workings we've done so far will still work. So we're figuring out where does the snake go. Then we're going to want, I guess, apple number. And again, that'll by default start off as 1. So that's, in other words, when we start off, we're looking for the first apple. So then apple, I guess, apple, let's call it apple right and apple down. So this is going to be index on these guys. $5. So that's just the address, and then I want to convert this into how far right, which is going to be mid. So in other words, I want to skip the letter, so I'm going to say mid 2 2. So start at character 2, meaning skip the first letter, and I'm going to take 2 characters because there could be a 2-digit number. And if I try to take the second and third characters from something that only has 2 characters, like I4, then I'll just end up with the second character, so that's fine. And then multiply that by 1 to turn it into a number. So in other words, if it's I4, then I'm in column 4, because a little confusingly, the letters go down and the numbers go across in this snake grid. And then for this one, I need to convert it to a code, and then, so that means A will be 65, so I need to subtract off 64. So that's telling me I4 is the ninth row, which is right, and the 4th column, which is right. So then I need to figure out whether I get this apple. And then I'm just, yeah, let's just start with that. So get apple. So there's never an apple in A. We start off in A1 and there's never an apple in A1. So I never have to contemplate the possibility that you will get the apple here. So I'll just make that by default 0. Then we'll say the apple number is that plus that. So in other words, if I ever say yes to getting an apple, then we'll move on to the next one. This part can stay the same. Now, so does the move from 1 1 to 1 4 take in the cell 4 9? So I guess there are two ways it can do that, which kind of overlap. So in other words, it can come down to it or through it, or it can come across to it or through it. So yeah, so we'll just say equals or. So I either need it to be in the same, now I'm confusing myself, having referred to these as right and down to feel intuitive, but now I'm thinking of them as rows and columns, and of course how far right you are is the column, not the row. So anyway, either you're the same amount to the right, and then it goes from above you to below you, or below you to above you. So the apple's rightness is equal to the snake's rightness. Then the apple's downness is less than or equal to the max of the before and the after downness, and the apple's downness is greater than or equal to the min of the before and after downness. So those are all the conditions for the apple to be hit vertically by a vertical move. And then we just want to do the same thing for the apple to be hit by a horizontal move. So that's the second part of the OR, which is another AND. So in other words, you can hit it vertically if you're in the same column and you go, you know, the starting and ending points are respectively above and below or matching. And then same thing here, you need the row or the downness to match, and the rightness or the column to be less than or equal to the larger of the two, the from and the to, and greater than or equal to the smaller of those two. So then we close the AND, close the OR, and that tells us we did not hit the apple, so carry on. Oh, and there we go. So on this one, it's telling us we hit the apple. So, and yeah, we actually end up right on top of the apple at 4, 9. So let's just take a look at this. We go 3 down, 7 right, 1 down, 4 left, 4 down. That's a lot to remember. Let's just, I find it helpful to just completely work, or follow one out to make sure it's working. So first we go 3 down, then 7 right, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Then we go 1 down, 4 left, 4 down. So 1 down, 1, 2, 3, 4 left, 1, 2, 3, 4 down. And sure enough, we are in I4 at that point, and we eat the apple. So that's good. And after that, we're looking for apple number 2, which is in 1912. And we can carry on down, and we can figure out, okay, actually we never hit another apple. So this sort of simplistic approach is then done. We can say apples eaten, and that's just going to be COUNTIF on this column true. And actually, I guess I should have made that false since I'm making it a true-false column. But again, if you go to add trues and falses with numbers, then true is equivalent to 1, false is equivalent to 0. So it's kind of either or works fine. So then we just need to data table that for values 31 to 50. So I'm going to go 20, starting at 31. Data table that. Column input cell is the picker. And we're going to hit calculate. And that is what that comes up with. Now, sorry. The question I want to ask myself is, I'm going to copy these and value paste them here. Is there any case where that answer is wrong because it does not account for the possibility of eating 2 apples in one move? I think I just about have the energy left to get through that, and then I'm going to do a sort of hacky version of level 4 and skip level 5 entirely, and do a sort of here's one I made earlier. So this is V1, and then I'm going to, let's see. So then I'm going to have to add here the next apple rightness and next apple downness. And that is just going to be this. Let me just check quickly. What's the most apples that I hit? The max is 6. So I'm not coming anywhere close to eating all of the apples. So I don't need to, basically I was wondering, do I need to worry about having error checks here for if the number gets above 20 or anything like that? And the answer is no. We never come anywhere close to eating all the apples, so that's fine. So I'm just going to not have any error checks. I'll just do this. And instead of J5, I'm going to say J5 plus 1. So in other words, I want the address of the next apple. And then same thing here, copy that over, J5 plus 1. So you can see now 1912 is the address of the next apple, and sure enough, after I've eaten an apple, that clicks in over there. So we come down here, and then the question is get 2 apples. And how will we figure that out? Well, first of all, I'm going to say if this, because if that's false, then if that, maybe, otherwise, definitely no. So, in other words, on this turn, you might hit a second apple. So then, the way I'm going to work that out, let's see. If I lock in the columns of these references and these references, then I can copy this formula over to here, and then I'll have a check for does it pass through. So then I'll say if it hits the first apple and the same move passes through the second apple, then I'll also need to check the direction works. It's a little bit complicated, but it's doable. So I need to lock in the references for G and H. So G and H and H and H and G, G, 2 more G's. Okay, so then we copy that over here. and then I want to add in this piece. So let's move this one back up to point to this row. And my maybe is going to be this whole mess. And then I'll need an extra check for direction in a minute. And then my no is just going to be the word false. And now actually one thing we could do is just, we can do a check straight away to see does that ever add a second apple? Because if it never adds a second apple, then we don't need to check. And if it does add a second apple, then we need to check, was it going in the right direction to actually get the second apple? So I'm going to say plus M5 plus P5. Copy that down. So you can say V2 here, and then V3 will be the one with the direction check if I need it. So let's refresh. Oops, sorry. So interestingly enough, it looks like the answer is that never changes the answer. So this is one case in which you would not be rewarded for rigor. But the nice thing about this is in the exam you get to, or in the kind of live challenge, you get to drop your answers into the thing and you can see if you've got full marks, and if you haven't, then you can go. So that, I guess there's an argument here as a strategic point that if there's an ambiguity like that where it might make a difference, then you are better off to, as quickly as you can, do a first pass and then come back after to refine it if needs be. And actually, I'm just realizing as I look at this now, there was a much faster way to figure out that this logic was never necessary, which is I looked here to see, does this ever get above, does it ever get up to 20? But I figured out the maximum, the highest number of apple you ever eat was 6. Well, the first time we ever get a repeat is between apples 7 and 8. So if you never get to apple 7, then you never have to worry about eating apple 8 in the same move as apple 7. So there you go, classic example of me overthinking. But the good thing about it is if you build it the simple way first, then you can always drop your answers in, and if you get all the marks, then you can just say, okay, great, dodge a bullet, move on. All right, so very quickly, I'll show you the kind of slightly hacky way to do level 4, and then I'll do here's one I made earlier on level 5. So I'm just putting some empty white spaces. I want 2 sets of 5. So basically, I'm going to convert these into into a pair of coordinates again, as I have before. And the reason I added an extra 1, so there's 5 apples to hit, but I want to start off at A1, so that's why I added an extra 1 for 1, 1. So then this is going to be, let's just say my down, and this is going to be my right. So my down is the letter, so I'm going to say code of this minus 64. So C is 3, that makes sense, good. And then my right is going to be mid this 2 times 1. And then again, there are edge cases here that might kind of make me wrong on 1 or 2, but the sort of 90% of the way their answer is to say just a kind of straight taxi cab distance. So in other words, if you think about, if I'm here and I want to get to here, it is almost certainly going to take me 1, 2, 3, 4, 5, 6, 7, 8, 9 moves. There are some weird edge cases where that might not be the case. So let's say if I want to get from here to here, and if I'm facing in the wrong direction, then I would have to go out, down, and back in. So it would take me more moves. But I think that's basically the only case. Otherwise, the direction you're facing in is irrelevant. Like in this case, if you're facing up, you turn right first and then go down. If you're facing this way, you turn this way first and then go that way. And if you're facing this way or this way, then you can just carry on until you get to a turn. So the sort of 90% of the way their answer is to say this. Let's just see how far we move for each move, and that's going to be equals the absolute value of that minus that plus the absolute value of that minus that. Oops. and we copy that down. Sorry, went one too far there. Kill that one. All right, and then hopefully this 49 will just match this sum, and it does. And do the same thing there. Now the one sort of immediate edge case to think about adjusting for is we start off in cell A1 pointing down, and so if we start off here pointing down, then our first move is to here. Then if the first apple is in row A, then in that case we would have to come across and then back up, and so our distance from 1 to 8 would not be 7, but it would be 1 down, 1 up, and 7 across. So my kind of getting from the 90% solution to the 95% solution is going to be that plus 2 times left this equals A. And so you'll see there here, so the first few it doesn't change the answer, and then here 57, oops, it does. I'll bump it up to 75, and I think there's another A down there. And again, I haven't actually checked the answers, but I would bet you that 90% of those would be correct. And then I'm probably a little over half an hour into this video. I didn't check exactly when I started, so were I competing, I would definitely not have time to hit level 5. No chance at all. So what I will just very briefly show you is an attempt at level 5 that I made a while back, because like I said, I was testing this question before the exam, or before the exam sounds very schooly, but anyway, before the competition. And so obviously if you're testing, then you need to make sure that all the answers are right. So I did at some point, not at all in half an hour, build a solution to level 5. So just to remind you, level 5 is, there's a sequence in which 50 different apples appear. You follow the strategy that we talked about earlier of, minimum cells and minimum turns to get from one place to the next. And the question is just how long can you do that before the snake hits itself? But obviously because you're following that strategy, it will never hit a wall. So yeah, like I said, this one was hard. So this very briefly is how I put it together. So basically to handle the snake hitting itself, rather than, so this setup here, I had kind of one row per move. So in other words, in this move it moves 7 squares, in this move it moves 1 square, in this move it moves 4 squares. The way that I decided to handle the snake, the potential of the snake hitting itself, was instead to have, each row would just be one block, and that way you could say, well, at move 12, what is the location of the snake? Well, or so what are all the locations of the snake? Well, in this case, it hasn't eaten any apples so far, so it's just this location, which is whatever, 8 down and 5 across. And if I come down to where, so like let's say here where I've eaten 5 apples, then at this particular move, my snake is currently in this location, this location, this location, this location, this location, and this location. Yeah, because so in other words, I've got I start off with 1, and then each apple I eat adds 1 more, so I've got a total of 6. So if this location matches any of the previous 5, then the snake is hitting itself and we've got a problem. I couldn't think of, I mean, in theory you could maybe use sequence with something like this to map out, here are the 7 addresses that this row hits, here are the 10 addresses that this row hits, but I couldn't find an easy way to think of kind of referencing back to the right number of steps. So that's why this one kind of takes up a lot more space. I mean, it breaks after you run out of apples or after you hit yourself or whatever. So that's why it's all ref errors down the end. So what is it doing? Well, first of all, we figure out what direction we're going in, and we're told we start off in 1-1, aiming down, and the first apple we're aiming for is apple number 1. So I check the apple's location, how far down and how far to the right, and then I look at the down difference and the right difference, in other words, the direction. So I'm at 1, I want to get to 8, which means that I want to go down. So you can use sign here. Basically, that's saying if how far down the apple is greater than how far down you are, then that difference will be positive, and so the sign of it is 1. If, let's just say we were at 5, or let's say we're at 9, so the apple is now above us, then you'll see that difference 8 minus 9 becomes negative, and so the sign of it is -1. And if we're in the same row as the apple, then the sign becomes 0. So this thing which says sign of how far down you are versus how far down the apple is just, it's kind of like an if, but with three possible outputs. So 1 means you need to go further down, -1 means you need to go further up, and 0 means you're already in the right row. And same thing for the right difference. 1 means you need to go further to the right to get the apple, and 0 means you're in the right column, and -1 means you need to go further to the left. So then I added a direction index here. So down is 1, up is 2, left is 3, right is 4. And so then I can say, okay, so am I further in the current direction or not? So this is how far is it in the actual direction that I'm facing. So because I'm facing down, then this is, so if I'm down, then it's the down direction. If I'm facing up, then it's the negative of the down direction. If I'm facing left, then it's the negative of the right direction. If I'm facing right, then it's the right direction. And so that allows me to figure out, if this ever becomes 0, then it's time to turn. So in other words, here I start off in 1, 1, then I go 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, and then at 8, 1 I'm in the same row as the apple that's in 8, 20. So that becomes a 0, and that's the signal here to turn. This whole turning formula is really complicated. I'm not going to explain that. So then I go from 8, 1 to 8, 2 to 8, 3 to 8, 4, until I get to 8, 20, which is where I hit the apple. So then I get a yes on the apple. I add 1 to my apple count. So just running count plus whether I got one on that one, and that's what I then reference to figure out the size of my snake later. And then I've then got the location of the next apple, so that if I hit this one, then I can figure out which direction do I need to turn to get this. So the next, given that I'm at 820, the next apple is above me and to the left of me, and so from where I am, it is. So I'm currently going to the right, so I need to go back the other way, which means I'm going to need to turn up first and then go across. And so that helps me figure out, okay, so now this arrow needs to go up. And then you kind of run it on down until at some point the snake hits itself. So that's what this self-intersect check here is for. So actually the ref errors are where you get past the end of all the apples, but in this case it's hit itself before it gets all the apples. And so you can see here, I'm basically saying if I'm on turn 1, then 1. I don't know why I have a 1. 02. Oh, sorry. Yeah. So in other words, if it was already a self-intersect, then keep it that way. That's what that's saying. So if the previous row is 1, then keep it as 1. Otherwise, count ifs to say how many of the previous, and we're using of all the previous ones where the row number here is no more than the number of apples I've eaten away from my current location. So in other words, has this spot been visited in the past n turns, where n is the length of the snake? And at some point that will say, yes, you've hit yourself. And I mentioned that I like to kind of visually work through one example. That was hard enough in this game that I actually ended up making this funky little visualization here, which says, okay, snake starts off in A1, first apple is in 820, so H20, and then you can just scroll it along and watch the snake game play itself. It's vaguely hypnotic. Probably better if it would go slightly faster, so that and you can see the light orange is where the next apple is going to be, so you can see how it turns itself, and it goes on, and you can see it's getting longer and longer. Sooner or later it's going to run into some troubles, but not for a while yet. It is very hypnotic. And then at some point here it'll show you an example where the next apple is already inside the snake. Oh yeah, there. So let's just go back. So here you can see, whoops, went too far. So back one, only one. Yes. So here it's going after this apple, so it's going to go down here and eat that. The next apple is going to appear here. That's actually going to be on the snake. Boom. But that does not count as being eaten until the head of the snake gets to it. And then, yeah, here we are at last. So having eaten 30 apples, boom, the snake crashes into itself, and that's the end of the game. Anyway, it took me a very long time just to even give you the cursory overview of this. So you can imagine this was, I did not think that it was realistic that somebody would solve level 5 in half an hour. And I didn't think it was worth trying to do it myself on a Friday night. But I'll give you the tour of the old way anyway. That's all I've got for today. I will see you next time.